So we continue in our introductions to mathematical statistics. So today we'll be checking some solutions to some exercises in the fixed sections that we have checked. Or you can just pause this video and look at the previous videos. So here we are going to solve some problems from the textbook we are using. Okay, so question number 1, that's 1.21. The textbook we are using is Introduction to Mathematical Statistics, 8th edition. Alright, so we have find the union C1, C2, and the intersection C1 intersection C2 of the two sets C1 and C2, where A, we have C1 to be equals to 0, 1, 2, and then we have C2 to be equals to 2, 3, 4, and then we have C1 to be x such that 0 is less than x is less than 2, and then we have C2 to be equals to x such that 1 is less than or equals to x is less than 3, and then C, you have C1 equals to x comma y such that 0 is less than x is less than 2, 1 is less than y less than 2, and we have our C2 to be equals to x comma y such that 1 is less than x that's less than 3, and then 1 is less than y less than 3. So obviously the union of these two guys is equals to 0, 1, 2, 3, 4, and then the intersection is equals to is just 2, just 6 singleton set. Then for this we have C1 union C2 it's to be x such that is from 0 to 2, this from 1 to 3, then there will be 0 less than x less than 3, and then the intersection of that guy, we have this is 0, 2, and this is 1, then the intersection should be x such that 1 is greater than x is greater than 2. Okay, then we have greater than or equals to, nice one. So we have that, and then this the union of these two guys will be x comma y such that for the x value, x as x, this from 0 to 2, 0, 1 to 3, then this will be from 0 to 3, and then for the y, this from 1 to 2, 1 to 3, and then this from 1 to 3. So then the intersection should be what? So this from 0 to 2 for x as x is 0 to 2, 1 to 3, then we are going to have from 1, because this does not contain 0, 1 to 2, and then for the y as x, this is 1 to 2, 1 to 3, then we are going to have 1 to 2. Alright, this is very simple. So let's check the next question. There's problem 1.22. So we have find the complement. C prime of the set C with respect to the space X to the space C if A we have our fancy C. So this respect to the fancy C equals to X such that 0 is less than X less than 1, and then our C equals to X such that 5/8 is less than X is less than 1, and then B we have our fancy C to be X comma Y comma Z such that we have X squared plus Y squared Z squared is less than or equals to 1. Then we have our sample space X Y Z such that X Y squared Z squared is equals to 1. And then we have for C we have X comma Y. So we have mod X what's the absolute value Y less than or equals to 2. So that is a diamond. And then we have a circle such that X squared plus Y squared is less than 2. Okay, so for this, obviously the complement, if you chop off 5/8 from here, then this the complement should be X such that that will be from 0 to our 5,8. So this point does not include our 5/8, so that's why we include 5/8 at this other side. Alright, so for the second one, we have the complement. So this a volume, okay, spherical shape. So our sample space include all the circle center at 1, but this sample only includes 1. So the complement of this will be only include the inside and not the boundary. So this include the boundary, then this what will be left will be the one that does not include the boundary. Okay, so if we check this one, we have something like this. We have a center at root 2, a disc with a center at root 2, where we have a diamond in this point. So if we draw the diamond of this and cut off this part, so the remaining part here, very tricky, but just have to be very careful. The remaining part here will consist of all points in this point that are not here, and that means that this have to satisfy X squared plus Y squared less than 2, and then the absolute value of x and y have to be greater than 2. So the point distance is greater than 2 here, and then the half part of this. So this means our complement is the region of the disc outside the diamond. Okay, so let's move to the next question. There's 1.23. List all possible arrangements of the 4 letters M, A, R, and then Y. Okay, we have let C1 be the collection of the arrangement in which Y is the last position, and then let C2 be the collection of the arrangement in which M is the first position. It's in the first position. Sorry, should be in. Sorry, here we're in the first position. So we have to find the union and then the intersection of C1 and then C2. So the first is to list out the possible arrangements. So the possible arrangement here we have 4 letters, and then permutation of 4, that's 4 times 3 times 2 times 1, and then they are going to have 24 possible outcomes. So for a fixed M, so we are going to look for fixed M, for 6A, for 6 fixed R, and for fixed Y. Then each of them should have 6 elements, and that will complete our possible arrangements. So for M we have A, R, Y, then M, R, A, Y, then M, R, Y, A. Okay, then M, A, Y, R, then what else we get? We need 2 more arrangements, so we can have M, Y, R, A. Then lastly we have what? We have M, Y, M, R, M, A. Okay, let's see, we need 1 more possible arrangement. M, A, Y, R, M, Y, A, R. Okay, so for A, so we have A, M, R, Y, A M Y R A R M Y. So we have A R Y M. There remain four possible arrangements. Two possible arrangements rather. So we have A Y M R. There remain one possible arrangement. A Y R M. Okay. So for R, we have R A M Y R A Y M R what now? So let's have R M A Y R M Y A. So remain two possible arrangements. So we have R. So we have R Y Y A M R Y M A. So for Y, we have Y R A M Y R M A Y A R M Y A M R, then Y. So we have Y M R A, then Y M A R. Okay, so that's the four possible arrangements. Then we have C1. So the C1 here, we have C1 be the collection of the arrangements in which Y is in the last position. So Y in the last position, we have this, we have this, we have this. Then there's Robert. So there's all. So you have Mary. You have Emery. You have Harmon. Oh, we have one more here. Then we have Amri. Sorry for that. Okay, then for C2, so we have C2 to be the collection of arrangements in which M is in the first position, and that is the whole of this. That is Mary, Emery, so we take the union of these two guys. So we have Mary. So that will be the collection of everything we have. That will be Mary, Emery, we write this okay. Now we have to be very careful now so that we not repeat the element twice. So here now we are not going to include those points at which where Y is added large. So we just have to include those points, those elements where Y is not in the last position. Whereas we have a repetition. So we have this, we have this, then we have this. So for the intersection, so those are just the points where y is in the last and then m also is in the first position. That will be mirroring, and that will be what else? M1. Then we are done. So let's check the next question. So next question we are going to check is 1.26. We have show that the following sequences of sets CK and non-decreasing. Then we have to find their limit k tends to infinity c of k. Alright, first we have ck equals to x such that 1 over k is less than or equals to x less than or equals to 3 minus 1 over k, and k equals to 1, 2, 3, dot. So b, write this in black. B, you have ck x comma y such that 1 over k is less than or equals to x squared plus y squared less than equals to 4 minus 1 over k, where k equals to 1, 2, 3. So for the first a, so we know that a sequence is increasing. A sequence non-decreasing if ck is less than or is a subset of ck plus 1. And okay, so if you check our ck is given to be x such that 1 over k less than x less than or equals to 3 minus 1 over k. Then our ck plus 1 will be x such that 1 over k plus 1 is less than x less than 3 minus 1 over k plus 1. Okay, so for a simplest one, you can just check when k equals to 1, when k is equals to 2. And then that should be sufficient for it to justify these two claims that they are non-decreasing. So for C1, we have x such that 1 over 1 less 1 less than or equals to x less than or equals to 3, and that will be 2. Then for C2, that will be half, and then this will be 3 minus half, and then that will be 2. Pardon, yeah, that will be 2 and the half. So you can see that this sets, the first one we have 1, 2, then the second one we have half, 2 and the half. So we can see that this is a non-decreasing function. Pardon, this is not correct. This increased to 2 and a half. This is half. Oh no, that's not true. We have this, sorry for that. 1 comma 2. Then the next one we have half. Then we have this 2 and a half. So you can see that this is a non-decreasing function as the function is getting bigger and bigger. So for that now, the limit ck tends to infinity. So since this is non-decreasing, then our limit will be the union. Okay, yeah, it will be the union of k equals to 1 to infinity of ck. So for sufficient large k, we are going to have x such that we have x such that we have 1. This very large k, this is 0, 0 less than x less than 3 minus 0, that also will be 3. Okay, alright, so for b, let me rewrite that. We have ck equals to x comma y and then 1k less than or equals to s squared and y squared less than or equals to 4 minus 1k. So you also check this, you see that ck plus 1 is comma y such that 1 over k less than equals to s squared plus, so this k plus 1 is less than 4 minus 1 over k plus 1. So you will see that obviously our ck is a subset of our ck plus 1. Or you can also prove that by checking for c1 and c2. So the limit of this also k tends to infinity of ck will be union of k equals to 1 to infinity ck. So for sufficient large k, we're going to have s comma y to be, this will be 0 less than s2 y2 less than 4. So we have that, and then we are done. So the next question is question 7. There is 1.2.7. We have shown that the following sequences of set ck are non-increasing. And then we have to find the limit. Find limit k tends to infinity of ck. Here we have ck equals to x such that 2 minus 1 over k is less than x less than or equals to 2, and then k equals to 1 over 2, 3. After that we have b, we have ck equals to x such that 2 less than x less than or equals to 2 plus 1 over k 1 over 2 over 3. That's so. For part A, our ck is given to be x equals to, s such that 2 minus 1 over k is less than equals to 2. So you see that our ck plus 1 x such that 2 minus 1 over k plus 1 is greater than the previous one. Okay, if check for C1, so if check for C1, you have 2. This is half closed. For C1 we have 1, we have 2 minus 1, we have 1, we have 2. So for the other one, this is 2 minus half, and that is 1 and the half. So you can see that obviously this is non-increasing. So this is non-increasing because this is also, so the second one also will be at this point, and then this also will be 1 and a half. So it will be somewhere, they just assume it's somewhere here. So the third one, we see that it will be moving in decreasing, and then decreasing. So the limit of this k tends to infinity. So for the proof of this, we have ck plus 1 is a subset of ck. So that means that the function, or sorry, the sequence is non-increasing. Alright, then the limit of non-increasing function, sorry, if we set, is given to be the intersection yeah, we have the intersection of this, and that will be equal to x, such that for large case this will be 0, this will be 2, less than x, less than a equals to 2. So what does that mean? Since this is 2 and this is less than that 2, that means that we are going to have a single point x. Going to have a single point 2. Okay, so for B we have secant to be x such that 2 is less than x less than or equals to 2 plus 1 over k. So obviously this is also a non-increasing. Why? Because ck plus 1 is a subset of ck. So you can also test that by checking for k1 and then k2. So you have something like this. We have this is half closed 2 for the first one, for ck, and for c1 rather, we have 2, this is closed, then 2 plus 1 we have 3, then the other one still 2. For C2 we are going to have 2, but this is reducing, this should be 2 plus half, so this is shrinking also. So for large k, limit k tends to infinity for ck. For sufficiently large k also, we are going to have x such that x is greater than 2, is also less than 2. So obviously this is just 2. Okay, so we have one more question. We have ck equals to x comma y such that 0 is less than x squared plus y squared less than 1 over k. K equals to 1, 2, 3. So we check this also. So if we do for the ck plus 1, fxy is less than x squared plus y squared plus 1 over k plus 1. So this also ck plus 1 is also a subset of ck. So that's for any k. I noted. So the limit of this also will be the intersection of k equals to 1 to infinity c of k, and that will be x comma y just as 0 is less than x squared plus y squared. For sufficient large k, this also restricts to 0, and then obviously this is 0. This is just an empty set because we are dealing with 2 points and then we are getting 0. Okay. So let's see. So we can continue to check let's see, can we, okay, let's make it a little bit faster. Question 1.28. Yeah, for every one dimension set C, I will define the function k of c to be the sigma c f of x, where our f of x is given to be 2 over 3, then 1 over 3x equals to, and s is equals to 0, 1, 2, then 0 x-ray. Okay, and I have if c1 equals to x such that s equals to 0, 1, 2, 3, and then c2 equals to x such that s equals to 0, 1, 2, So we have to find q of c1 and q of c2. Okay, so let's see. So q of c1, so we really have x equals to 0 to 3, that will be 2 over 3. Then substitute the value of x. We have 1 over 3 to the power 0 plus 1 over 3, 1 over 3, 2, 1 over 3, 3. Then this is equals to 2 over 3, 1 plus 1 third, plus 1 ninth, plus 1 third, then 1 over 27. Then you can finish up this. So for the second one, we have QC2 equals to, so this is infinite because we have 0, 1, 2, 3, So for this, you can just factorize 2 over 3. Then you have 1. We have the next, we have 1 over 3. The next 1 over 3 square, 1 over 3, 3. So int here is just to make use of the sum of sum of infinity of a geometric series. You have xn equals to a over 1 minus l. Your fixed term, so you have 2 over 3. Your fixed term here is 1, and the common ratio is 1 over 3. And then you have 2 over 3, 1 minus 1 over 3, that will be 2 over 3. So if we turn this up, then this should be equals to 1. Alright, so that's a nice problem. Okay, so we will continue in the solutions for the remaining exercise in the next video. I hope to see you there. Don't forget to subscribe and share with fellow statistics students. Thank you so much. See you.